Welcome to Chapter 28, Reflection and Refraction. Of course, we're going to talk about reflection and refraction. We're also going to talk about the principle of least time, the law of reflection, the causes of refraction, dispersion, rainbows, total internal reflection, lenses, and lens defects. Now, we say light is reflected when it's returned in the medium from which it came. The process is called reflection. When light illuminates a material, the electrons in the atom of the material will move more energetically in response to the oscillating electric fields of the illuminating light. The energized electrons re-emit the light by which you see the material. Now, in shiny materials like metals, those electrons produce a very well-defined, what we call a specular reflection, that it looks like the reflection in a mirror. And that's because the electrons are loose, and that's the same reason that they conduct both heat and electricity so readily. Now, the idea that light takes the quickest, least time path and going from one place to another is called Fermat's principle of least time. It's sort of like me when I commute. I have a 40-mile commute each way to work. I'm really good at taking the fastest path. Doesn't matter to me if it's a little longer, but I want to get there in the least amount of time. So I'm a lot like light. Now, finding the shortest time for light to go from A to B by reflecting off a mirror. So you want the light to go from here to here by reflecting off of this surface. So we're going to construct on the opposite side of the mirror an artificial point called B prime. B prime is exactly the same distance from the surface as B is. And of course, this is called a normal. A normal is a line that is perpendicular to a surface. You're going to be using normals a lot here, and whenever you measure an angle, it's going to be measured relative to the normal. So the shortest distance between A and the artificial line here through C is the straight line right through here. This straight line will intersect the mirror at point C, and that's exactly where the light has to bounce off the mirror to reach point B in the least amount of time. Now, there's some definitions here. The angle of incidence is the angle made by an incoming ray in the perpendicular. We always measure angles relative to the normal. The way I like to say it is we normally measure angles relative to the normal. If you accidentally forget and measure it relative to the surface, unless the angle has to be 45 degrees, you're going to get it wrong. The angle of reflection is the angle made by the reflected ray in the perpendicular, which is the normal. The normal actually stands for perpendicular. The normal is an imaginary line perpendicular to the plane of the reflecting surface. It lies in the same plane as the incident reflected rays. And here is a diagram of that. Here's the surface that you're reflecting off of. And here's the incident ray. Here's the normal. There's the angle of incidence. Here's a reflected ray. Again, here's the angle of reflection relative to the normal, not relative to the surface. The law of reflection says the angle of reflection equals the angle of incidence, or theta I equals theta R. Where, of course, this is theta I and that's theta R. The law of reflection applies to both A and B, light and sound. And if you've ever heard an echo, you've had a sound reflection. So sound is a wave and it can reflect too. Plane mirror images are virtual images. Plane is a flat mirror. That's the typical mirror you have on your wall. They are the same size as the object. They form behind the mirror. They're located in the position where the extended reflected rays converge. Now, don't be too worried about the reflected rays. Okay, and the extensions, we'll talk a little bit about that. We do more of this in Physics 122 than we do in this class. The image will form exactly as far behind the mirror as the object is in front of the mirror. So this is the distance to the object, that's DO, equals DI, which is distance to the image. And all these distances are measured relative to the mirror surface. This is a virtual image. The light will not actually pass through the image. It's a construct of our mind and eyes. There's actually nothing back here except just what we imagine is back there. And if we put a screen here, you wouldn't see anything. Now notice the image is upright. Whenever you see an upright image, it's almost always a virtual image. If it's upside down, it's almost always a real one. So here's a mirror, and we're looking at an object in the mirror, and we see an image back behind the mirror. When an object is placed in front of a plane mirror, an image of the object is formed in the mirror. The distance of the image from the mirror is the distance of the object from the mirror. So that is this distance right here. And that equals the distance to the image, the distance that the image appears behind the mirror. And this cannot be formed on a screen. So you can't put a screen back here and see an image. So this is called a virtual image. It's not really there. It's just a construct of our eyes. Because we think that all light moves in straight lines. We don't realize it actually is bending off the surface. So to us, we form this image back there because in our brain, light moves in straight lines. And there's the straight lines to construct the image. Now, a plane mirror is a flat mirror. Now, notice, if you look at this, we always think everything's backwards in a mirror. In reality, the only thing is reversed is front to back. Now, you don't have to have a flat mirror. You can have one that's curved. And the easiest thing to look for a curved mirror is a shiny spoon. On one side of the spoon, the side you scoop up the cereal with, you have a concave surface. It looks like a little cave. concave surface. That's the side you eat from, the side you scoop up your cereal. If you flip the spoon over, you'll have a convex mirror. Sort of like I like to think of that if you are sleepy and you pick up the spoon the wrong way, how vexed you're going to be when you don't get any cereal off of it. Yeah, because it all rolled off the backside of the spoon. So the shape of the mirror will form different virtual images. A convex mirror, that's the backside of the spoon, is one that curves outward, and this will only form virtual images, and the virtual images are always smaller and closer to the mirror than the object. So the distance to the image is less than distance to the object. A concave mirror is one that curves inward. It's like what you look at the side of the spoon that scoops up your cereal. The image can be larger and further away than the object, and then it's a virtual image. It'll be upright then. Or it'll be closer and smaller than the object. That's if it's real, depending on how far away the object is relative to a point called the focal point. Now, a concave mirror is also called a converging mirror because it converges light. So here we have parallel incoming light coming into the mirror, and it will bounce off the mirror using the angle of reflection equals the angle of incidence. And when you do that, you bring these rays all together. They come together at a common point called the focus. The focus is located at distance f, little f, from this side of the mirror here. That's this distance here. If instead you used a compass and you wanted to draw this curve, you put the needle of the compass right here and the pencil right there. That would be the curve. The radius of that curve, of that mirror, is called the radius of curvature, and that's r here. And it turns out that r equals 2f, in case you're curious. And of course, f is the focal point and f is the focal length. C is the center of curvature, r is the radius of curvature. Now, concave mirrors, when you put an object somewhere between here and here, within the focal length of the mirror, so distance of the object is less than the focal length of the mirror, the image is right side up. That means it's a virtual image. It is enlarged. It's behind the mirror. The image is further from the mirror than the object. So you put the object here, the image will form back here somewhere, and it'll be bigger than the object is. So distance to the image is greater than distance to the object. Now, if you have at home, besides a spoon, you may have a magnifying mirror. And if you look in that and you get that close to your face, you're going to see an upright image, and it's going to be bigger than your face. If instead you move it away, you put it further than the focal length of the mirror. So you can do this with a mirror. Have it close up so that you can, and look at your image in the mirror, and then gradually move it away. You'll come to a place where suddenly the image gets really blurry. When the image gets really blurry, you are actually putting the object right here. And the reason it's blurry is because the light rays are coming out parallel. So you can't focus parallel rays. Your eyes can't do it. If you keep on moving further away, your image is suddenly going to flip over and be upside down. At that point, you are further away. You're outside the focal length. So you put your object out here somewhere, and the image is upside down, so you're going to end up with a real image. The image is larger than the object when the object is close. In other words, when it's less than 2f, so when it's within this area here, by the way, 2f equals r. The image can be equal size when you have the distance to the object equals 2f. So if you're at the center of curvature, right there, the size of the image will be the same size as the object. The image will be smaller than the object when the object is at a distance greater than 2 times the focal length of the mirror. So beyond the center curvature, the image is smaller than the object. The image is real. Any light passes through the image. You can put a screen there and you would actually see an image. Now, there's all kinds of uses of a concave mirror. Besides the magnifying mirror, the makeup mirror, and the shaving mirror, dentist mirrors are concave mirrors. Headlamps and spotlight reflectors behind the lamp and the spotlight, you'll see a curved reflector surface. That's a concave mirror. And telescope mirrors are concave mirrors. These are called reflecting telescopes. They all have concave mirrors. That's the mirror right here. And this is basically what they call a prime focus reflecting telescope. If you take Astronomy 111, you'll get to see that. Now, the other main type of curved mirror is a convex mirror. Okay, it's also called a diverging mirror because it diverges or spreads light. So parallel light coming in here will bounce off the mirror and will all come out diverging. They're spreading out. If you take the reflected rays and extend them backward through the mirror, they'll all come to a common point called the focal point. And the focal point is behind the mirror. So you can guess that this is going to form virtual images. Now, in a convex mirror, the image is always right side up. It's smaller than the object. It's virtual, closer to the mirror than the object is in front of it. So distance to the image is less than distance to the object. So you put the object out here somewhere, say you put it here, the image is going to be formed closer to the mirror than the object did. So distance to the image is less than distance to the object. Here's a security mirror. Okay, see how small the stuff is? Now, what are these useful for? Well, they're useful. You ever see the passenger side car mirror? And it says down at the bottom, objects in the mirror are closer than they appear. Well, that's because our eyes measure distances by the relative size of objects. And if the size is small, it's going to look like it's further away. And you can see that in this here. All these objects look small to us. So they look like they're further away. This guy looks like he's standing 30 feet away. He's probably only 10 feet away. And these are wide view mirrors. They show a wider field of view than any other kind of mirror. So you can see what's going on in the corner near the beer coolers. And they're useful for, as I mentioned for security mirrors. For that very reason, you find these things any place where there's like a party store or convenience store. They want to make sure nobody's stealing beer from the cooler. The light reflecting from a smooth surface undergoes a change in none of the above. It doesn't change frequency, speed, or wavelength. Now, there are two basic types of reflection. There's specular reflection. That's the kind you get from a mirror. Then there's also diffuse reflection. And this occurs when light strikes a rough or irregular surface and reflects in many directions. Still, the angle of incidence equals the angle of reflection, but the surface is rough. So when it reflects, instead of reflecting coming off all at one angle like it does for a specular reflection, like a mirror, it comes off at many different angles. And that's called diffuse reflection. Now, you've probably noticed this. You're downtown in your car and you're listening to the radio, old-fashioned radio, and you drive past buildings and the radio seems to fade in and out and maybe gets us kind of like a ghost, and some places are stronger and some places it isn't. Well, then you've experienced this. Old-fashioned ghost images that would occur in old-fashioned over-the-air TV. Not so much likely to see that anymore, but you can still see it in radio. Now, what is a rough surface? It actually depends on the wavelength of the light. Usually, a surface with irregularities of size less than 1/10 of a wavelength is polished or reflective. This is a radio telescope. Notice that the light goes right through it. Light has short wavelength, so these holes in the radio telescope let light right through. But radio waves have very long wavelengths. These holes are much smaller than 1/10 of the wavelength. So to a radio wave, this looks like a polished mirror. And you can see this in the door of your microwave oven. If you look through the door of your microwave oven, there's a screen in there. It's got little holes in it. The wavelength of microwave radiation is at least 10 times the diameter of those holes. But light has such a short wavelength that the light goes through the holes. But to the microwave radiation inside the oven, that's a mirror. Now, different road surfaces can determine the amount of diffuse reflection. A rough road surface has a lot of diffuse reflection. So you can see the road ahead of the car at night. A wet road surface is smooth, and because it's less diffuse, it can be difficult to see. It can also be very annoying when headlights glare off of it. So it's very hard to see. Not only should you slow down in wet conditions because the road becomes slippery, but you also can't see as well. So there's another good reason for slowing down in bad conditions. Diffuse reflection occurs when the sizes of surface irregularities are large compared with the wavelength of reflected light. The rougher the surface is, the more diffuse the reflection is. Now that's reflection. Be very careful. Now we're going to talk about refraction. When light bends going obliquely from one medium to another, we call this process refraction. So you have light coming in. Here's the angle of incidence relative to the normal. It enters a different medium. And light slows down when it enters different mediums. You either slow down or speed up. It depends on the density of the material. And the density of the material is related to what really occurs, and that's called the index of refraction. Water is a denser material. Light slows down in dense materials. And therefore, it wants to spend less time in here. So in order to do that, it has to bend closer to the normal. We'll talk more about that later. Remember, light always wants to take the path of least time. So it always tries to follow a path that minimizes the time it takes to get from point A to point B. So suppose you're a lifeguard and somebody in the water gets into distress. And you have to decide how you're going to get to this person as fast as possible. You want the principle of least time. But you're smart and you know you're like light. You know that you can travel a lot faster over the sand because you can sprint over the sand at maybe 13 to 15 miles an hour. Swimming in water, you're down to about 2 miles an hour. So you want to make this path as short as possible. So you spend the least amount of time in the water because it's the slowest medium. It has the highest index of refraction. It's a slow medium. Here, you're fast. So you want to do more distance here to minimize the total time it takes you to get from point A to point B. That's what light does. It doesn't go in a straight line necessarily. It bends to accommodate itself, to make sure that it takes the least amount of time to get from point A to point B. Now here we have glass. Glass has a higher index of refraction. It's a slower medium than air is. And if you got the light just coming in straight, parallel to the normal, that's the angle of incidence is 0, nothing happens. It doesn't bend. Because there's no advantage here to shortening. You can't shorten the path. There's nothing you can do here. But instead, if it comes in an oblique angle here, remember it's always measured relative to the normal, comes in an oblique angle here, it's going to be further away from the normal in the fast medium because this path length is longer. When it encounters the slow medium, the glass, it has to slow down. So therefore, it's going to bend toward the normal to make this path shorter. See, this path through here is shorter than that one would be. So it's going to bend toward the normal. Now it comes out of the glass back into the air. Now it's back. Ooh, I'm back on the freeway. I can take a longer path. So I'll bend away from the normal. It's sort of like me when I come into work. If I know the freeway's moving fast, even though it's a longer distance, I'm going to use the freeway because I know it's moving fast. I'll get there faster. This is kind of like what happens when light encounters a change in medium, a change in speed. So the bending of light when it passes from one medium to another is caused by the change in the speed of light in the different media. Speed of light is a characteristic of the material. It's also a characteristic of the wavelength in the material too, the wavelength of light. So the way to look at this is sort of like you have a loaded grocery cart and you decide for some reason to take a shortcut through a patch of grass. You're coming in at an oblique angle here. It's not along the normal. And what happens is when your cart, the wheels of your cart encounter the grass, this wheel's going to slow down more than that one will. So this one's going to outrun this one. And it's going to have a tendency bend toward the normal. So there'll be a torque produced on the wheels that will push the cart toward the normal. The same thing happens when light goes from a fast medium, like air, into a slower medium, like water. The light will slow down, because this always stays perpendicular. These are the wave fronts. The ray is perpendicular to the wave fronts. When this wave front slows down, the ray bends toward the normal. So refraction is a bending of a ray of light when it passes into or from a material which has a different density. That's a different index of refraction, and we call that index of refraction N. So here is an incident ray coming in. Here's the angle of incidence, always measured relative to the normal. It's going from a low density to a high density. And when it goes into high density, it slows down. The index of refraction is higher, light is slower. So it wants to take a shorter path. It does so by bending closer to the normal, so the angle of refraction is less than the angle of incidence. Now, if it's perpendicular to the surface, there's no shortcut, there's nothing to be gained, so there's no bending here. But there will be if it's at some angle other than perpendicular to the surface. So from low end to higher end, such as from air to water or glass, water has a higher index of refraction than air, so light will travel more slowly in the water and will change direction at the interface. The light wave will bend toward the normal. Air has a low density, low end, so it's fast light. Water has a higher density, high end, so it's slow light. So in this case, the light will bend toward the normal. So the angle of refraction is less than the angle of incidence. If we're going from high index of refraction to lower index of refraction, such as from water to air. Air is less dense than water because air has a lower index of refraction. So air is a fast medium, water is a slow medium. So the light will travel more quickly in air, and therefore it will change direction. And because it can afford to have a longer path length, it will bend away from the normal. So the water has a higher density, higher index of refraction. It's slow. So it's going to be closer to the normal. Slow light's always closer to normal. Air will have a lower density, lower index of refraction, and it's fast. And that means it will be further away from the normal. Remember, you're always measuring relative to the normal. The angle of refraction is greater than the angle of incidence. It is called the refractive index, otherwise known as the index of refraction. We give it the symbol N. It indicates how much the speed of light differs from its speed in vacuum. It indicates the extent of the bending of rays. It's the ratio of the speed of light in a vacuum to the speed of light in the material. And be very careful. A lot of people mistake this and flip it. So it's C over V, where C is the speed of light. That's 3 times 10 to the 8 meters per second in vacuum. V is the speed of light in meters per second in the material. V is always less than C, so N is always greater than or equal to 1. In a vacuum, N equals 1. In air, it's 1.002. It's almost equal to 1, but not quite. It's slightly greater than 1. Glass, it's usually like 1.5. Water is 1.33. So in equation form, N is the speed of light in vacuum divided by the speed of light in material. A medium with a high index of refraction has a high bending effect. It's going to bend more further away from the normal because it's moving slow. When this is small, when the speed of light is small, when it's slow, that makes N big. So that means you have a high index of refraction, and it will bend further away from the normal. So here we have a flashlight. We shine it in some water. It bends toward the normal as it encounters the higher index of refraction, bounces off a mirror. Angle of incidence equals angle of reflection. Comes out of the water and bends away from the normal again. It doesn't matter whether you take this light path or you take that light path. They're fully reversible. You can see this for yourself. You and your buddy are looking at each other in a mirror. He can see you and you can see him. So light can go two ways. It's fully reversible. Now, refracted light that bends toward the normal is light that has slowed down. If it's bending to anything that's closer to the normal has slowed down. Refracted light that bends away from the normal is light that has sped up. Anything that's further away from the normal has sped up. Now, there's all kinds of illusion that is caused by refraction. For instance, our eyes and our brains think that light travels in straight lines, and we're hardwired for that. So we really can't think any other way. If you try to catch a fish underwater with your hands, it's very difficult to do because the fish looks like he's here. Instead, he's deeper. He's about 30%, 33% deeper in the water than he looks. So objects submerged in water appear to be closer to the surface. Now, this is what makes driving through floodwaters so dangerous, or walking through floodwaters. Water's deeper than it looks. Water that's 3 feet deep will only look like it's 2 feet deep. So people misjudge the depth of water all the time because of this. Our brains think it's a straight line, and it's not. Okay, it's bending toward the normal. There it is. They're bent toward the normal. This angle's less than that angle. So that makes this fish really down here, and he looks like he's there. So you should never drive or walk through floodwaters, ever. You don't know what's down there, and you don't know how deep that water is. Water moving a few miles an hour at the 6 inches deep floodwaters can knock you off your feet. It only has to be 6 inches deep to knock you off your feet. What it does is knocks your feet out from under you. That's really what it does. Water that's about a foot deep can push a car off the road. And on top of that, the water can undermine the road. You don't know how deep the water is, and you don't know whether that road surface is still there. Most fatalities occur in floods, and people drown in their cars. So please don't do that. Turn around, don't drown. Don't walk through floodwaters. And also, you don't know what's in them either. Don't walk through floodwaters. People have gotten electrocuted walking in water. Okay, now there's other kinds of illusions caused by refraction. Do you realize when you look at a sunrise or sunset and you think the sun is just touching the horizon, the bottom of the sun, called the lower limb, is just on the horizon? In reality, the whole sun is under the horizon. Because of this fact, this refraction, okay, air, for its tiny little index of refraction, it's almost the same as vacuum. But you're looking through a lot of air here. This is a thick layer of atmosphere. This might be 200 miles of air. That slight bending is enough to make this half a degree below the horizon when it looks like it's sitting on the horizon. So in reality, hours of daylight are slightly longer. Okay, now if you've ever been driving down the road on a hot, sunny day, sunlight is beating down on the road surfaces, and you look down the road and you see something that looks like a puddle of sky shimmering on the road. That's a mirage. Okay, now what causes a mirage? Well, when air heats up, it becomes less dense, more like a vacuum, so its index of refraction drops. So therefore, it can take the longer path through the heated air close to the road surface. So it will bend like this. And the way you can think of that is it always bends away from the warmer air. It bends toward the cooler air up here and away from the warmer air down there. So it's a good way to remember that because light speeds up in the less dense material. This is called a mirage. And what happens is the sun has heated up this surface. So the light will bend like this. So you're looking at a distant palm tree here, and your brain says that has to be a straight line, so the palm tree is upside down under the sand. What happens here instead, you're seeing the mirrors, the surface, you're actually seeing the sky. You think you're seeing a puddle on the road, instead you're looking at the sky. And it shimmers because of all the heat waves, okay, that are rising through this, that are changing from minute to minute, changing the index of refraction. Now this is called illuming, and this occurs when you're looking past over a surface that's cooler. Cooler air is dense, so the index of refraction gets higher when it's dense. It will bend toward the denser, the higher index of refraction, but your brain thinks it's a straight line. So this ship here to your brain is upside down and above the water. Now this is a way that you can actually see over the horizon. So you can picture this curved surface here. The ship might be over here under the horizon, but you can still see it. And that's really weird. I've seen that on the ocean. And that's called looming. And this is caused by the unequal heating or cooling of the air, changing the density of the air and the index of refraction of air. Now here's a coin in water, and it looks like it's about 33% bigger than the coin in air. It's the same distance away from you, but this one looks much closer than it is, so the water doesn't look as deep. This is why people drown when they walk through floodwaters. They misjudge the depth of the water, how fast that water's moving. I mean, it can be moving, 10, 20 miles an hour, and it looks like it's perfectly smooth. You also don't know what's under there. So this is what's going on here. The coin looks like it's here when it's really down there. So objects in water are closer than they appear because of water's higher index of refraction. So this is very dangerous. Never walk through floods or drive through them either. Now, suppose you're counting your fish in your aquarium. This is actually one fish. He's producing multiple images. You've probably noticed this in a pool, bottom of a pool on a sunny day. Okay, this is caused by the ripples of water. These act like little lenses and bring the light to focus, and that's what all these bright spots are on the bottom of the water. Now, it also makes the stars twinkle at night because the atmosphere is full of these little pockets of warmer or cooler air. And of course, the density affects the index of refraction. And these things in the air is constantly moving. And suppose you're looking at a distant object, like a star. And as these pockets of warmer and cooler air move past you through your line of sight, they will affect the way the light gets refracted. So this makes the starlight scintillate and twinkle. Astronomers hate twinkling stars. It's called seeing. If the stars are twinkling, it's bad seeing. If the stars are relatively stable, it's called good seeing. You kind of imagine why they hate it. They're looking at something with a telescope. They're measuring something very accurately, and the thing is jumping around in the image, especially when you magnify the image. It makes the star will literally hop around. Here's a picture of this. This is the same object. It's a galaxy. This is when the twinkle is bad. It's called bad seeing. Stars are twinkling. There's a lot of these pockets of air moving past. Usually occurs right after a cold front or a warm front has moved through. You end up with this furry, blurry image here. Here's a night when the stars weren't twinkling so much. It's a lot better. When light travels from one medium to another and changes its speed in doing so, we call this refraction. Now, dispersion is the process of the separation of light into colors arranged by frequency. It is caused by the fact that the index of refraction is also wavelength dependent for most material. So what happens is white light comes into a specially shaped medium, has a higher index of refraction than the surrounding air does. And when it does, the red light gets bent by a smaller amount than the blue light. So it separates the wavelengths of white light that contain all the wavelengths of light into their component wavelengths. And this can also be used in a diffraction grating. It's a slightly different way. In a diffraction grating, the blue light is bent less than the red light, but it still separates it. It's still called dispersion. So when white light enters a denser medium, the different colors are each refracted by a different amount, depending on the frequency. If you look at this, here's the wavelength of light. Here's red on the right, blue on the left. Here's the index of refraction, low index of refraction down at the bottom, higher index at the top. Notice that blue light on this side has a higher index of refraction than red light does for this particular material. Most materials are like this. The red light, which has the lowest frequency, is usually refracted the least. So it encounters each surface, it bends a little bit, but it's bent less than the yellow light, which is bent less in turn than the blue light. Blue light has the highest frequency, is usually refracted the most because the index of refraction is higher for blue. So blue is a slow light and red is a fast light. Now, this does not occur in vacuum. Do not fall for that. The index of refraction is completely wavelength independent, and it's always 1. It only occurs for transparent mediums. It's not for vacuum. When white light passes through a prism, green light is bent more than red light. Green light has a shorter wavelength, so it's going to be bent more. Rainbows are a result of dispersion by many drops. This is an example of dispersion of light by a single drop. Sunlight comes in, hits this change in media. The light will slow down as it enters a more dense media, but it slows down in different amounts for different wavelengths of light. It starts to disperse here, and it bounces off the back of the drop, comes over here, encounters another change in media, and bends again, a different amount. And notice that the violet light will disperse a different amount than the red light will. So it's basically been separated or dispersed. Now here's this example of sunlight incident on 2 sample raindrops as shown, and it will come out of them as dispersed light. Now the sun is behind you here, so the light's coming from back over your shoulder, and you look into the region where there's a lot of water drops. And we're just showing 2 water drops here. The observer will see the red light from the upper drop because the angle here is just right for the red light coming out of this water drop to reach his eye. He will see the violet light from the lower drop because the angle is just right for the violet light coming out of this lower drop to reach his eye. And there are millions of drops here. So they're producing the whole spectrum of light. And of course, the light from one drop is relatively faint, but if you've got millions of them, the rainbow will get brighter. Now, you have to have the sun back behind you. So your eye is located between the sun, not shown off to the left, and a water drop region. You're looking into a place where maybe it's been raining recently and there's a lot of water drops in the air. The rainbow you see is the edge of a 3-dimensional cone that extends through the water drop region. Now, most of the time, the cone is cut off at the bottom by the ground. Now, that is not true if you're up in the air. If you're in a plane, you can actually see the entire rainbow Normally on the ground, you only get to see half of the picture. When you're up in the plane, you get to see the entire rainbow. If you're ever up in a plane and you're flying over or near clouds close to sunset, and if you get lucky, you'll see the shadow of the plane on a cloud. And then surrounding that shadow is something they call a glory. Glory is just a complete rainbow, a whole circle. Now, all the drops that disperse the rainbow's colored light toward you lie in the shape of a cone of different layers with drops that disperse red your eye on the outside, then orange, then yellow, and so on, all the way to violet. Violet's always the inner circle here, the inner cone, and red is always on the outer cone on a primary rainbow. The thicker the region of the water drops, the thicker the conical edge you look through, the more drops you have and the more vivid the rainbow. Only rainbows along the dashed line, in this case, disperse red light to the observer at a certain angle. Hence, this light forms a bow. Now, observers in a position to see only a single color from any one droplet of water. Your rainbow is different from the rainbow seen by the others. Everybody has a unique rainbow. Your rainbow moves with you. So if you move, your rainbow goes with you. And this is especially true on a plane. The plane is moving, maybe 600 miles an hour, and your rainbow keeps up with you. The disk within the bow is brighter because of the overlapping of multiple refractions, which don't occur outside the disk. Now, you can also, if you get really lucky, you might see a secondary rainbow. It's caused by an additional reflection inside the drop. Now, here's the primary rainbow. Notice that the blue or violet color is toward the inside, the inner color, and the red light is on the arc, the outer arc of this rainbow. Notice here's the secondary rainbow. Notice that the colors are reversed due to that additional reflection. Also notice that the color is fainter because there are more refracted light loss and more reflections. So you end up with more light loss here. So the secondary rainbow is always reversed in colors and fainter than the primary one. Compared with the primary rainbow, the secondary bow is dimmer, has the colors reversed, and is caused by two internal reflections. Now, total internal reflection, otherwise known as tear. This is the total reflection of light traveling within a medium that strikes a boundary of another medium at angle at or greater than a certain angle called critical angle. This only applies if the light comes from the medium with a larger index of refraction. So you've got a flashlight and you're in water, underwater, and you're shining it up toward the air, toward the surface. Some of the light gets reflected off the inside of the water surface, and the others comes out and emerges and gets refracted as it goes through this change of speed. And because air is less dense, has a lower index of refraction than water, the angle of refraction is greater than the angle of incidence. Remember, the angle of incidence is always measured relative to the normal, and so is the angle of refraction. And of course, as you change this angle of incidence here, make it greater and greater, this angle of refraction also gets greater and greater. And it does so faster than the angle of incidence increases. Eventually, you reach a critical angle where the refracted ray, that's the one that's coming out of the surface, doesn't come out of the surface anymore. It lies along the surface, and that's called the critical angle. We'll explain that a little bit more in a few minutes here. So here we go. We're shining a flashlight. We're in here somewhere, right about here. We're shining a flashlight up from water into air. And when light enters the air, it speeds up because the index of refraction is lower. It speeds up, and then it bends away from the normal. Fast light is away from the normal. Slow light is closer to normal. Now, a small amount of light gets reflected back from the water surface from the underside here, and the rest of it gets refracted. The total amount always adds up to what's in here. We're assuming nothing gets absorbed. If we increase the angle of incidence, the angle of refraction will also increase, and it will increase faster. This angle here increases faster than that one does. So the angle of refraction increases faster than the angle of incidence. Also, the angle of reflection will increase. Less and less light gets refracted, more and more light gets reflected. So this beam gets brighter and that one gets dimmer. Eventually, you reach a point where the angle of refraction, that's with respect to the normal, right here, is equal to 90 degrees. And that means the refracted beam is lying right under the surface. And most of the light gets reflected back from the water surface. This is the critical angle for total internal reflection. So it should say critical angle for total internal reflection. If you're a fish underwater, this would be very important to you. You're a fish underwater and you look up toward the surface of the water. It turns out there's a cone about 97 degrees in angle where you can see what's above the surface of the water. If you look beyond that cone, the light gets reflected off the inside surface of the water, lower surface of the water, and all you see are the sides and bottoms of your pool. Okay, now there's some advantages to this. If we put glass in a prism, okay, we can use total internal reflection to internally reflect almost 100% off these inner surfaces here. And this is very useful in optical instruments. You ever notice the old-fashioned pirate movies and they're using a spyglass, long tube, and it's usually pretty awkward, and the guy is looking through it through his good eye when it isn't covered by the eye patch. He's looking toward the enemy ship to see what they're doing. He's spying on them. Humans are used to having binocular vision. It's really nice to be able to look through both eyes at the same time. And you could do this. You could tie two spyglasses together. But then spyglasses are heavy. Glass is heavy. And metal tubes are heavy. And they're awkward. They're long. Wouldn't it be nice to shorten those and compact those? Well, there's a way of doing this. It turns out that the reason that these spyglasses are long is because the image degrades if you shorten the light path. And it's very hard to get lenses that will not degrade the image if you had to shorten the light path. So what they do is they fold the light path up by using prisms and total internal reflection, because these things are very good at reflecting. They're better than mirrors in many cases. It effectively lightens the light path between the lenses. This eliminates the need for long barrels and binoculars. It makes them much more compact and easier to handle, and still doesn't let the image be degraded. And on top of that, the image in a spyglass is upside down, unless you do something to re-invert it. And a prism will do that. Or if you invert an inverted object, it's right set up. Okay, now this is also useful in optical fibers, fiber optic cables, and things like that, and what used to be called light pipes. Here are some thin, flexible rods of glass or transparent plastic. The light from one end of the fiber is totally internally reflected to the other end, and you can even bend this. So most of the light that comes in comes out, and you can see here's showing the light. There's a light source down here, and it's coming out up here. Now, what do they use these for? Well, do you have a car with an illuminated instrument panel? Behind your instrument panel, there are fiber optic cables. They're used for concentrating light in dental procedures. They're used for the viewing of inaccessible regions of organs and other devices. Say, suppose something gets stuck down in your drain pipe, or a sewer. They put this stuff down there to light it up, and they put a camera at one end so they can see what's going on at the other end. And it's useful in communications and in internet, fiber optic cables. By the way, it's very fast and very low loss. Now, image formation is a consequence of the light traveling in straight lines. The first camera was a pinhole camera, and it's very easy to make a pinhole camera. All you need is a piece of cardboard and a pin. And the best way to do this is to go outside and use it on the sun. Do not look through the hole. Don't look at the sun. Please don't do that. Instead, what you're going to do is let the sunlight shine through the hole. Hold the pinhole camera, hold your cardboard with a hole in it, about 3 foot off the ground, off a white surface like concrete or something like that. And you'll see little images of the sun on the surface. And the image will be upside down. In other words, it's a real image because you got to put a screen back there and you can see it. And the image is upside down. Now, I saw this effect during a partial eclipse of the sun. Pinhole images caused by small openings in the leaves above. And these are actually images of the sun. And during a partial eclipse, part of the moon covers the sun, so it winds up in a crescent shape. So there was hundreds of little moving, because the air was blowing these around, little moving images of the eclipse. It was really charming. Another way to change the path of light is to put it through a lens. A lens is just a transparent medium that will bend or refract light. A lens is a refractor. So a lens refracts the light passing through it. Lenses are refractors, mirrors are reflectors. So be very careful. There's only a 2-letter difference here. People get that confused all the time. So at any rate, here we have a magnifying lens. And we use magnifying lenses to produce a virtual image upright and larger than the object. So we can examine the virtual image in greater detail than we can discern in the object. So that's the reason it's called a magnifying lens, because it's a bigger image. There's some key features of lenses. Here's a lens. Here's the principal axis. The principal axis is a line joining the centers of curvatures of the two lens surfaces. The focal point is a point at which parallel rays will all come together. So if parallel rays come in from this side, from the left here, they'll converge on the focal point on the right. If parallel rays come in from the right, they'll converge on the focal point to the left. Lenses have 2 focal points because the light can go through the lens from either side, unlike a mirror where the light cannot go through the mirror. The focal length is the distance between the center of the lens and either focal point. And in most lenses, especially thin lenses, the 2 f's are the same on either side. There are 2 common types of lens. One is a convex or converging lens, and it is thicker at the center than it is at the edges. And it converges light, which is, of course, why they call it that. If you have parallel incoming light, the light gets bent and comes to a common point called the focus. And that'll be a distance f from the lens. The other is a diverging or concave lens. That means it is thinner at the center than it is at the edges. When light comes into this lens, it diverges. That's why it's called a diverging lens. Now, a convex lens will act like a concave mirror. It brings light to a focus. So in other words, when parallel light comes in, it will come to a common point called the focus. It produces a real inverted image of a distant object or a virtual enlarged image of a close object, just like a concave mirror does. We're going to model the lens as two prisms in a block of glass. So when light comes in here and encounters a slower medium, the glass is a slower medium, it bends toward the normal. And it goes through this part of the glass. When it encounters a faster medium, it bends away from the normal. The two bends together bring parallel light to the focal point. And of course, the light coming through this opposite side comes to the same focal point. A converging lens can project the real image onto a wall or screen. You cannot do this with a concave lens. So if you're looking at this slide and somebody's projecting this on the wall or on a screen, it's a real image. Why isn't the image that you see upside down? It's because they put something else in here to invert the light coming from here. And if you invert something that's upside down, it's right side up. Now, there are lots of uses for convex lenses. Magnifying glasses, I mentioned before, your eyes have two convex lenses, your cornea and your lens. Cameras often have more than one lens. Refracting telescopes, here's a lens and another lens. Okay, so this is the objective lens. That's the one that's closest to the object. And this is the focal length of the objective. Here's the eyepiece lens. That's the one you look through with your eye. Here's the focal length of the eyepiece. And you can see they're both convex lenses. Projectors also use convex lenses because it's the only way you can get a real image, the only way you can get an image onto a screen. And correcting farsightedness. If you are farsighted, okay, the image wants to focus behind the retina. And if you try to focus an image behind the retina, you're not going to see anything very clear because it has to come to a point on the retina to be in focus. Instead, you put a converging lens, which will shorten the effective focal length and bring the image to the retina so you can see it clearly. Now, a concave lens acts like a convex mirror. It takes parallel incoming light and diverges it as it goes through the surfaces. And when it does so, if you draw an extension of these emerging lines back, they'll come together at a point called the virtual focus or focus point, focal length, and that is a distance f on the same side of this lens as the light is coming from. So this produces a virtual upright image, and it will be always reduced. So it's just like a convex mirror. You cannot get a real image out of a concave lens. Now, if we model this surface as a couple things like this, parallel light comes in, it encounters the slower medium, and it bends toward the normal. When it comes out again and encounters a faster medium, it bends again away from the normal. The arrangement and grinding of these surfaces makes the light diverge. If you take an extension of this emerging ray and this one, they will meet at a common point called the focal point, and that is a distance f from the center of the lens. Now, concave lenses are used to correct nearsightedness. In the nearsighted eye, the image forms in front of the retina instead of on the retina. So you put a diverging lens in there to bring the image back to the retina. And notice it's upside down, and it's a real image. Otherwise, you couldn't see it in the eye. It wouldn't show up on the back of your eye, on your retina. The action of lenses depends mainly on refraction. Be careful not to get that confused. Now, there's all kinds of things that can go wrong with lenses, and any kind of defect is usually called an aberration. An aberration is some sort of distortion in the image. There are various types of aberration. There's one called spherical aberration. This is the result of light passing through the edges of a lens and focusing or diffracting in a slightly different place than where light coming from the center does. So notice that the focus of this part of the light coming from the edge is closer to the lens than the focus from the light coming further out. And this causes blurriness and maybe rings around distant lights. Chromatic aberration is a result of the various colors having different speeds and different refractions in the lens. So the index of different medium has a wavelength-dependent index of refraction. So they don't all focus at the same point. Typically, blue light bends more than red, so blue light will have a closer focal point. F for blue is less than F for red, because red light bends less, so its focus is going to be further away. For most materials. Astigmatism occurs when the front surface of the eyeball is unequally curved so that focus is unevenly. And it's sort of like those ripples you see on the bottom of a pool. Just that rippled surface of the pool is like an eyeball with astigmatism. Light takes a path from one point to another that is quickest. It always takes the path of least time. When light meets a polished reflecting surface, so far no reflecting surface is perfect. We're getting close, but it will partially reflect. Your reflected image in a plane mirror is as far behind the mirror as your distance from the mirror. The distance of the object is the same as the distance of the image for a plane mirror. To see your full height image in a wall mirror, the minimum height of the mirror should be 1/2 your height. The image of yourself in a mirror is actually reversed, front to back, and you can see this guy is straddling a mirror. The mirror is right here, and this leg is being reflected front to back. That's sort of what makes it hard to cut your own hair. You can never tell exactly what the scissors is. Whether a particular surface acts as a polished reflector or diffuse reflector depends on the wavelength of the light relative to the size of the surface irregularities. Refracted light that bends away from the normal is light that has speeded up. Atmospheric refraction occurs with changes in air temperature. The fastest light inside clear glass is going to be red. Don't fall for that. All light has equal speeds in vacuum. When light incident on a prism separates into a spectrum, we call the process, none of these is actually called dispersion. If you viewed a full circle rainbow from a helicopter at the center, you will see the shadow of the helicopter. The critical angle and total internal reflection occurs when incident light on a surface is refracted at 90 degrees to the normal. When a pinhole of a pinhole camera is made larger, more light will get through, so the image is brighter. Now, there is a limit on this. If you make it too big, you won't get a fuzzy image. A real image can be cast on a screen by a converging lens. A diverging lens can only produce virtual images, so you can't cast them on a screen. A converging lens can form either a real or virtual image, just like a concave mirror. The amount of light entering a camera or your eye is regulated by a diaphragm. That is, of course, the iris of your eye, which opens and closes the pupil to regulate the amount of light coming in. The glasses of a nearsighted person are usually thicker at the edges than they are at the middle. Eyeglasses can correct for light distortions called either spherical aberrations or chromatic aberration. Thank you.